In this video, we will outline a set of algorithms used to extract a path from a human-drawn input image. Our application of this process can be seen here, as a robot detects the input image in front of it and extracts the path. Then, the bot will trace out the path on a large sheet of paper, marking where it has been and producing an enlarged copy of the original image. Once the input image has been detected, the first step to extracting the path is to determine which pixels in the image are black and therefore part of the path. As you can see here, a thin black line may be difficult to see, depending on the marker used, the lighting and shadows in the room, and the distance of the camera from the paper. The k-means algorithm accounts for these factors by first assigning each pixel to one of two clusters, black or white, such that every pixel belongs to the cluster with the nearest mean grayscale value. K-means will find the optimal mean black and white values by iteratively assigning pixels to each cluster, then recalculating the means using updated assignments. Iteration stops when no improvements to the means can be made. After running k-means, we now have a connected graph of black pixels, in which any two black pixels can be connected via neighboring black pixels. This graph is too fine for the bot to traverse every node and edge, so the next step will be to generalize the graph into a path the bot can feasibly travel. Here, you can see our recursive algorithm traversing black pixels in the image, marking visited pixels in red. As each pixel is visited, it adds a new node to our generalized graph if the distance from the previously added node is great enough. The resulting graph has reduced our original of approximately 3,000 black pixels to one of about 100 nodes. The nodes of our graph then go through a refinement stage, where each node is centered on the line and bad nodes are removed entirely. Bad nodes are any nodes that are too close or far from their closest neighbor, which may result as flukes of detection or difficulty traversing intersections. We now have our final set of nodes for the graph, but we do not yet have edges connecting them. A naive algorithm would be to add edges in the order that the nodes were discovered, but this only works on paths like these that do not have intersections. The most interesting and challenging paths will have intersections, so our node connecting algorithm must take into account the slope of the path it is currently building. This way, when an intersection is encountered, we choose to connect nodes that are on a similar slope to that the bot is already traveling. While taking slope into account is effective, this method is still flawed. In some cases, the path with the best angle will skip over white pixels instead of following the black path. To avoid this, we use a variant of the wavefront algorithm to tell when a path segment illegally tries to cross white pixels. Each path segment receives a score determined by the slope and wavefront calculations, and the segment with the best score is added to the path. Once our path-making algorithms have run, we have an ordered path that the bot can follow. Thanks to k-means, the detection is resilient to changes in lighting, and the slope and wavefront calculations create a path that closely follows the original black line.